I'm coming at MBT kind of from the philosophy perspective,
Good.
and I'm very familiar with your work. I've been following you. I think I came across the London lectures in 2008 or something,
Hmm.
and I've read the book I think twice all the way through, but I go back to it a lot, watch your lectures and stuff. So I'm very familiar. So no need to go over the basics. So I kind of wanted to talk to you to try to ask a few questions that maybe you haven't been asked before, or things that I'm still kind of trying to figure out. I think I've got a really good grasp of your theory, but there's still a couple of little things. So I still
Okay.
want to touch on epistemology, metaphysics, the medium of experience. But first, I would like to talk about your experiments because I've recently um, kind of delved deeper into experiment one.
Hmm.
A friend of mine spoke to me about your experiment one and concerns that came up about those in the
Hmm.
past. And I listened to your audio, which was a response to those concerns. But also, I did my own research, and so the original concern was that you're never going to get um, an interference pattern on R3 where your screen is. Um, and that is a prediction made by quantum information theory, which is essentially what you're testing. You're testing whether or not the detectors determining the which path information causes collapse, or whether it needs to be made available to a conscious observer to cause collapse. Quantum information theory seems to say that it doesn't matter if it's made available to a conscious observer if it's determined by the polarizers or the BBO crystal or the calcite crystal. If it's determined, then it's going to cause collapse. So the concern was that your R3 screen is always going to produce a diffraction pattern. It's never going to produce an interference pattern. So that concerned me because I love experiment one. I've always wanted that experiment done. And I just assumed that, your setup was correct and it would be working fine. But when this was brought up to me, I was like, oh no, maybe I should look into this and make sure, see for myself. So I looked at your actual setup and the way you have it. It's a little different than the way it was presented originally, but I think that's just because it has to be that way. And after doing my own research, I've kind of convinced myself now that your experiment is going to succeed, and I'm very excited about it. But I kind of wanted to get your take on uh, the kind of the specifics of how it works, and I can actually bring up a screen share of the setup if you want.
Sure. Why not? If we're going to show this to other people, that would be handy so they would have some idea what we're talking about. No. Okay.
I don't know if that's accurate to the way you
Yeah.
have it set up now,
That's
but
pretty accurate. Yeah.
okay.
Except let's see, one change. There is a change in the way it's actually working now, but the change is kind of neutral. It doesn't cause things. Instead of sending a vertical or horizontal polarized signal, S, the bottom path, the blue path, it's sending a diagonal polarization, and then the filters, the P, the yellow and the pink, instead of being horizontal and vertical, are anti-diagonal. It's a 90-degree diagonal. And the reason for that was simply the equipment worked better. It was it was not theory driven, but driven by practicality. When we used that, we got better. We got more good data. So that's one change. Let's see. I don't think we're using a calcite crystal anymore. I think we're using some other sort of beam splitter that separates polarity rather than a calcite crystal. But basically, that is the idea. And a few comments about this experiment. If you look at the experiment, if we just look at the one that I briefed in my 2016 talk in Los Angeles, that's where I first presented these experiments, and I have pictures of that. It would be nice to show that picture in contrast, because you'll see there's a lot of things added in order to make the experiment work. I had a very simple experiment where you had photons coming at the slits. Then from the slit, you had a which way detector, and that which way detector would determine what slit it came through, and that which way detection would be recorded. So you had a which way detector on both slits, and that information was recorded or not recorded.
Right.
Now, when you have it that simple, I think it indeed will work exactly the way I say it will work. Well, what happens is that is a very difficult experiment to do. As you can see, all this complication. We have polarizers, crystals, BBO. We have all kinds of things that were not in my experiment that have been added to it. And when you add, particularly in this case that we're doing here, the polarizers, you add another element to it that then causes the standard quantum physics to come out the way they say. But it's because of the added elements. If you could just do the simple experiment that I have listed, then I think it would work exactly the way I say. But once you add all these things, and the good news is, Chad, is that we're just starting to get data now on this experiment. And I've got a couple of experiments in. When I mean experiments, it is this experiment, but you have to run it a lot of different ways. So this is one way to run it. Another way is to put the absorber further up front, just after it comes through the BBO crystal. Another way is to, do it with and without the polarizers. So there's all kinds of things that you can change here to try to find out what exactly is going on and why. And I'm in the process of doing that now. Last time I talked with Farbod, he said that he wasn't quite getting as good results as he was. So something got bumped, very minute. When you're dealing with light, it's very fast, it's very small, and you have wave, you have wave properties to deal with when you do things like polarizers.
Right.
So it's a different kind of experiment. And I'm now kind of say, well, yeah, but what if this and what if that? And I'm looking at what standard quantum physics says and what I say, and kind of David, who's doing this experiment with me, he's kind of the devil advocate. He's playing the part of the standard quantum physics, and I'm playing the other side. And we kind of going back and arguing and seeing, what happens. And what I found is that if we could just do the simple experiment that I'm talking about, which doesn't have all of these extra things added to it, I think it would work just like I say, just as I say. And I don't know that that's impossible, but it seems to be very difficult. And what I found out is I've gone through the way that standard quantum physics explains these experiments, and I've taken several of the experiments. The first one being the one published in 2000. I think it was finished in 1999, but the publication wasn't until 2000. That was, let's see, it also, I'm trying to think of the guy's name. Anyway, that escapes me right now, but it was a similar thing. It uses an entangled pair, and then it uses the one path of the tangled pair to develop the which way data, and the other as the particle goes to the screen. It did not have polarizers in it, but in the very end, it did show no interference pattern, okay, but on the screen. But that's a little misleading. And the standard quantum physics CC there, just as we predict, there's no interference pattern. But if you look at, that's one where you do coincidence counting.
Right.
And if you look at the coincidence counting going through the two detectors that determine the which way data, you find out that there is a diffraction pattern produced by each slit. So if you look at that, you say, okay, when I say diffraction, you say diffraction to mean particle. Sometimes people say diffraction to mean interference. So we probably ought to not use the word diffraction, because the interference pattern is also a diffraction pattern. So let's talk about either a wave pattern and a particle pattern, or an interference pattern and a particle pattern.
Okay.
Okay, so that each slit, if you looked at just the photons that went through slit A, they fell into an interference pattern. And if you look at just the particles that went through slit B, they fall into an interference pattern, just as I predicted. The difference is that there's a phase shift. There's a phase shift of pi between them. So when one's up, the other's down. And when you put the two of them together on the screen, you get nothing. Okay, because everywhere there's an up on one, there's a down on the other. They're waves that are phase shifted pi. That's 180 degrees.
Right. So a
So
friend.
they're directly out of phase. So when you think about it, A and B both did produce interference patterns, just like I said they would. But the result of the slit is a combination of those two, which it always is. What you get on the screen is always the combination of where the electron went through, A slit, and where the electron, the photon, goes through in B slit. So it's always that way. So at the slits, my theory was correct. That was what you did get an interference pattern produced by each slit, but it just so happens they're pi out of phase, and that's why you don't get an interference pattern at the screen. So you see, I would kind of count that a win. The pattern you get from each slit is indeed as I said. Now, why do you get this phase shift? Well, there's lots of different reasons, and in my estimation, they all have some problems. The one that is held up by most of the quantum theorists, I've seen at least 3 different reasons for the pi shift, which when there's 3 different reasons, that tells you that they all really don't agree. 3 different reasons. So it just comes out in the math that there's a minus sign someplace, and that minus sign causes the phase shift. But I know how physics works and how physicists work, and they tend to modify the equations to suit the answer. That's just, they look at it and say, oh, well, look, this should have been a minus sign here, and that explains it. And they had a justification of why that was the case. But so I don't really believe any of those. So I think, in a sense, I'm verified there, because we do get interference patterns from each slit, and they just happen to be out of phase. Now, this experiment that we're doing here has the same problem. If you look at what goes through each slit, you get interference patterns. If you look at the pattern on the screen, you get the two interference patterns out of phase with each other. So it looks like it's a particle pattern. It's just no humps, because every hump was met with a dip exactly about the same size. So it's that sort of thing that's going on, and that's because the reason that you have these phase differences in my experiment is because of the polarizers. That's what causes the phase shift. So I pulled the polarizers out, and I got a beautiful interference pattern. And anyway, so I'm just in the process of, of working these kinds of things out. David and I are. So hopefully in a month or so, when we've kind of exhausted what we can learn from this experiment, I'll be publishing all of that.
Right. So one thing, I'll share my screen again. So, and if you just look at this portion where you had the polarizers originally,
Mm-hmm.
what I was looking into, so if you didn't, so here you have the horizontal at A and the vertical at B, and then you've got the
Right.
diagonal right before the screen.
Mm-hmm.
Um, so from what I was looking at, if you don't have the diagonal there, you get exactly what you were talking about. You get the particle pattern, and that's from the fringe interference pattern and the anti-fringe interference pattern overlaid on top of each other.
Yeah, or another way to say that is that you have two sources. One's, for one slit it's horizontal, the other slit is vertical, and those two can't interact. Those two waves are orthogonal to each other. Neither one can have a vector, on the other. So they just can't interact. You're taking two sources of light that cannot interact and produce an interference pattern because
Okay.
they have to interact with each other to produce an interference pattern, and they're orthogonal to each other. So that's basically just an optics thing, not really a quantum physics thing. So that's
Right.
why that doesn't work. So you
Now,
put the P, the green one there,
yeah.
which then takes both of them, will produce a component for the horizontal will have a component in the diagonal direction, and the vertical will have a component in the diagonal direction. Now you have something that can. But let's say that those polarizers cause some phase shifting, because we have to look at an actual wave. An actual wave is like, think of it as like a sine wave, right? You get a sine wave. It has a positive peak and then a negative peak, and then a positive peak and a negative peak. So I don't know. Let's see. Let me get this thing I have up here out of my way so I can see my own finger here. You have a vector goes up and down and up and down. So it's going up and down as the trig function goes, from 1 to 0 to -1 to 0 to +1 and so on. That's what the sine wave is doing. Well, those are going through those things. Well, now when it gets to that, so you got a horizontal and you've got a vertical, and do we know that they're in phase when they go through when they both hit this diagonal? Is one of those at the up part of its cycle in its way, in the waveform, the wave cycle, or was it at the down part of its cycle? Well, if they're opposite, then you've got that same problem again. You'll get them out of phase. So even though you're supposed to get a pattern that way, and you do, if they both, the vertical and the horizontal both have exactly the right phase in them. One's hits this peak this way as it hits the horizontal peak that way, and then the components will all line up. But if those components don't line up, then you'll get those two that'll be just opposite each other. So then, even with that setup, you may not get an interference pattern. That would be possible. It just depends on the details of how each wave, what part of its phase it is. So now we're talking about things that happen at half a wavelength. A wave shifted just a little bit one way or another. Now, if you're real careful, I suspect that it will work most of the time if you're sure that your light is precisely coherent. But by the time you run it through something like a BBO crystal, then kind of all bets are off. That changes. You're running it through a crystal. The speed of light inside that crystal is slower. So how thick's the crystal, and what does that do to the phase? So if you just have a coherent light and the polarizers, you'll probably always get an interference pattern with the horizontal and vertical will probably be lined up just perfectly together.
Right.
But when you stick crystals and other things into the mix, calcite things, you're changing things. And I don't know that that's necessarily accounted for as it should be. And then it would be possible to look at that setup you just showed me and not get, an interference pattern.
Right.
So there's other details we have to look at, and that was what I started off saying. If you just look at the picture that I put on my 2016, say here's the experiment, that's so simple and pristine because it's theory. It's not the practicalities that you have to go through to actually do the experiment. And that theory, I think, will work exactly as I say. But once you add all the complications that you need in order to actually make a measurement of the which way data, now suddenly you've got a handful of variables that you didn't have before. And that kind of, is kind of changes things. And you've got things going on like that phase difference between them.
Right.
I have another reason why there's a phase difference of pi. It has nothing to do with a minus sign anywhere. And that, I think, the reason that there's a pi phase shift there is that the detectors in that experiment, there was a D1 and D2 were the detectors that
You're talking about
detected
the delayed
the
choice quantum
Sully,
eraser from
yeah, right, delayed quantum eraser, Sully et al.
Okay.
Sully, Kim, Wu,
Right.
and 4 others. It was D2 and D1 were the two detectors that detected particles that were then erased. By the way, they had fancy little mirrors and things that erased the which way data. The particles, you had the which way data erased. And those erased data went to 1 and 2.
There you go.
Yeah. So it's D1 and D2 after the particles were erased, right? So now the way they set up this experiment is that every so often, you get something out of that pump and it's very regular. So you regularly get a photon that comes there, goes through this process, and goes into one of these 4 detectors, D1, 2, 3, and 4. And that process is constant. It's just, like you could think that every second a particle comes out, And if you look at the count, in D1 and D2, you realize that count, the sum of D1 and D2, has to be a constant. The number of counts you get in each one of those when you run through the coincidence counter, you're getting them at a constant rate. So D1 and D2, sum of D1 and D2 have a constant rate. Well, if they have a constant rate, then each one produces its own interference pattern. But if they were in phase, then you'd have to go a whole lot of counts when you're at the peak and not many counts when you're at the bottom. You couldn't have them coming regularly. You couldn't have consistent counts like they do. So because they have consistent counts, then you have to have a phase shift of pi between those two so that the result produces data evenly, consistently, just like the counts. So that's another way of looking at that problem that doesn't have a minus sign that somehow got changed to suit the problem, or any of the other things that they say are the problems. None of those actually make sense either. This one actually makes sense. The physics would tell you that you have to get a result that is uniform in the data rate, because the incoming data rate is uniform. The outgoing data rate has to be uniform. Can't change that. And the only way to do that is if there's a pi phase shift between them. So in any case, you see, my simple experiment has not yet been done, and I'm thinking it's very hard to do. In order to do these experiments, you need all kinds of other things. You need BBOs and prisms and beam splitters and all this other stuff these beam splitters, sometimes, they transmit, sometimes they reflect. But when they transmit, there's phase shifts. Every time you reflect, I think there's a pi phase shift. And when you transmit, maybe there's no phase. And there's other things that happen. You get a pi over 2 phase shift. So it becomes a very complicated mishmash of things going on. And the fact that if you look at all the particles that go into D2, which is where the data was erased, and all the particles going into D1, look at those separately and look at all the particles on the screen that went through, let's say, D1, you'll get an interference pattern. And you look at all the particles on the screen that went through D2, you'll get an interference pattern, just like I said you would. But because they have to be pi out of phase, because of the way the experiment has been set up, then you look at the screen and, oh, you get a particle pattern because the 2 out of phase interference patterns make a particle pattern. So that's kind of what's going on and where we are. And I'm trying to squeeze as much information out of this experiment as I can. But I'm afraid it's not going to be as clear as what I would hope it would be. But when I do my other experiments, the experiment, what is it, 3 and 5 or whatever, I got a couple of other ones that are rather dramatic, and they're more dramatic than this one. This one was just to try to understand how that, what was going on there. What was the difference between what I'm saying and what the physicists were saying? Why do we get this different answer? So I wanted to do this experiment so I could manipulate the details of the experiment to try to figure out really what was going on. And we're doing that. We're doing that now. And so far, what I'm finding is if you look at the individual slits, you get just what I predicted. And if you take those 2 individual slits and put them together, those patterns together at a screen, you get what they predict. So, that's the way it comes out. Now you'd think the pattern that goes through a slit. Okay, here's the pattern. The particles that go through the slit fall in this pattern, an interference pattern. The particles that go through that put themselves in an interference pattern. So you would think that the answer would be, well, they both produce interference patterns, but they sum to nothing, no interference pattern. So
Right.
that's where we are. It's still a little confused. I think they would claim that they were right. At the screen, there certainly was no interference pattern, but not because there was no interference. There was interference in both slits. Just as I said, they get no interference pattern because of the mechanism, the way in which they had to make the experiment work. That's why they're not getting, that's why they're getting this. And it may turn out to be is necessary. It may be that in order to measure that which way data, you have to do things to it that will always cause a pi phase shift at the end. That you'll somehow have to use polarizers or beam splitters or other things. And you'll always be using these particles that are entangled. See, I don't have any entangled particles in my thing. I just have particles, and you measure the which way data. But if you do these other devices, because of the way you have to use those other devices, you may always get that pi phase shift. So in which case, we're both right in a sense. I'm right at what goes through each slit. They're right at what you finally get at the at the screen.
Are you aware of, when I was looking into this, I found an experiment also by Scully done in 1991. They call it the SEW experiment. So it was Scully, Englert, and Walther. They did something that's similar to what you're trying to do, and it doesn't use entangled pairs and polarizers. they actually use a cesium atom, and they send it through a double slit. Well, first they energize it with a laser beam uh, after the slits, and then they send it over. I forget the name. It's some type of a cavity that will detect which slit it came through by absorbing a photon from the cesium atom. Have you heard about this?
No, I've not seen that.
Um, so they actually have what it can do is they can detect which slit it came through with the cavity that it passes over, and then they can actually erase the information by having the photon that gets sent into one of the two cavities be absorbed by a photon absorbing wall that's in between them.
Mm-hmm.
And so what happens is when they do that, when it hits the back slide, they still get an interference pattern, even though the witch path information was detected, it was just erased before it hit the back slide. Uh, and an interesting thing about this experiment is they also did it where they did a delayed choice, where they erase the witch path information after it hit the backslide. And in that case, you get the particle pattern, which was interesting. Um, so I don't know, I might have to send you that paper if you want to look it over, but
Yeah, well, that makes sense. That's the way it should work, I think.
right.
I think that's pretty much in agreement with me.
Right. Yeah, one of the things about the Kim et al. Delayed choice quantum eraser experiment is it seemed a lot of people make it seem like it suggests that there's a retro causality happening.
No, it's not the case.
Right. And so yeah, I would like you to talk about that because it seems like there's never any retro causality.
No,
Things are affecting things in the past, right?
no, no, that's what's going on there. You know, it appears as if there's retrocausality because you change something, you decide whether to erase or not erase the which way data after the particle has already impacted the screen. So as far as the what's on the screen, that experiment's already over. And now you decide whether you're going to erase or not erase, the which way data. And if you decide to erase it, then you get an interference pattern. And if you decide, not to erase it, you get a particle pattern. And how is it that you can do something after the experiment's over that changes the result of the experiment? That's kind of the problem. And it sounds like retrocausality. You've gone back and changed the results of the experiment afterwards, after the experiment was done. Well, the way it works is that, let me put it another way. The problem here in thinking is that there are particles, that this is a material reality and there are material particles. And when those material particles do whatever they do, well, that's the way it is. And, that can't be changed. Well, the way the world really works is there are no particles. There's only probabilities. So you might want to call those things not particles, but potential particles, protoparticles. It's not, you see, and there are no particles. That was the whole point of the double slit experiment is, they decided that the only way to make logic sense out of the experiment is if there are no particles. Particles don't exist. There's only probability. And those probabilities remain just probabilities, which means the particle is just potential particle until the measurement's made. And that's what requires, a human to make the measurement, or maybe you could train a dog to make the measurement. Just some consciousness need the data. Okay, so if you think of that particle and those particles and what they did on that screen, until the measurement's made, somebody looks at the screen. Those are just protoparticles, quasi-particles, or however you want to say it. Probability, a probability of a particle being somewhere. Now, when you decide later that you're going to erase the which way data, okay, now the probability is that you'll find those particles in an interference pattern. So you do the erasing or not erasing before you look at the results on the screen. That's the key. See, these experiments are all run, they collect all the data, then they start looking at the coincidence counter and sorting everything out. Then they find out what went where. So the answer to that is no, we don't go backwards in time, but you have to realize that particles really don't exist. They only exist in probability until the measurement's made. When the measurement is made, they look at the data and, that data says, okay, when the measurement is finally made, when you look at the screen data, say, where is that screen data? Well, now the experiment is all over. All the particles have already been counted. All the times have been recorded. It's all done at that point. And because there was no which way data, then you're going to get an interference pattern. That's the way, when you look at the screen data, that's what you'll find it, because that's what happened, 10 milliseconds or 10 nanoseconds, after it hit the screen, then either got erased or didn't get erased. So that's the answer to that. It's that there are no particles. There's just probability. So what's on that screen, even though that screen should already have particles on it, remember, they're not particles, they're just probabilities. And those probabilities change depending on what happens, whether the which way data gets erased or not. Those probabilities change. So, which means what's on the screen changes, because it's just probability. So you can't change particles. If you got physical particle there, then you can't say, well, the physical particles somehow change. That's retrocausality. But if you really don't have any particles there, you just have a potential for particles to be somewhere. And that doesn't get sorted out until after the which way data is either erased or not erased. Then that probability ripens, becomes a fact, and that's what you see on the screen. So that's the explanation for it. It's not a retrocausality thing at all. It just seems that way because materialists believe in particles, and that when particles hit a screen, by God, they're going to stay wherever they are when they hit there. That's a materialist viewpoint. But if you say, well, when probability gets to the screen, it's not yet, all the calculations aren't done yet as to what those probabilities are. And now, if you look at the screen first, if somebody was looking at that screen as the particle hit it, if somebody was sitting there at that screen, say, there's a particle. Now, that particle would have to stay there. Doesn't matter what happened. See, that's my other experiments, my later experiments. This is what I do. I put an observer looking at that screen to see the instant of where it hits. And then I can predict whether it gets erased or not. Because if it happens to fall in a particle pattern, then I say, oh, it didn't get erased. The which way data will be collected on that one. Now here comes the particle, and I can say, well, when it gets to this point, it's going to reflect, not transmit at that beam splitter, because it's going to have to say that particle was collected, there at number 3 or number 4. So those are my later experiments. I put an observer right there at the screen, and then that observer can predict what's going to happen at the mechanism that does the erasing or doesn't erase. It'll say, oh, now that entangled particle is going to transmit through that and go through the eraser process because this landed inside of an interference pattern. And what I do is I run the experiment just by itself for, I don't know, a long time. So I got a real strong pattern. So I know exactly what it is. And then I look at the statistics and I find if a particle lands here, what's the probability that that's part of a interference pattern or part of a particle pattern? You see? So I have it all mapped out ahead of time. and what the probabilities are. So if you land right in the middle of a peak, well, you're going to have a probability of 1 that's interference. If you get a high count there. If a particle lands right between peaks, well, that's going to be a space where that's where there are no peaks. So if you map that out, you know exactly where the peaks and dips are going to be. And then you can say where it lands. Here's the particle. Where does it land? Oh, that one landed right on a peak. Okay. So now you start saying, well, I'll count that as a peak particle. Now it might not be. There are some particles that just kind of make a fuzz at the bottom. There's some noise or some other things like that. But the statistics will follow you. So if you do that, you'll be able to predict, say at 70% accuracy, what happens when it gets to that beam splitter. Does it reflect or does it transmit? Well, that's impossible.
Mhm.
See, because that's just a photon getting to a beam splitter, and we know that's random.
Mhm.
That's random by nature. How can I predict that? The only way that can be predicted as if there is some awareness in the system that knows what the right answer is ahead of time. You see?
Mhm.
Bingo. That's what makes that experiment significant, because it not only makes a good point for particles being probability distributions, which that to me is obvious. There's only one good explanation for how that could ever happen, and that's that this is a virtual reality. How else could particles be probability distributions? It's a probability based virtual reality. There is no other answer for that. That's the only rational answer. So we got that already. And then on top of that, now we have consciousness as the computer. There's some evidence for consciousness as a computer, because something smart enough to know what's going to happen next, decides whether that's going to reflect or not reflect. And I can tell you what that's going to be, but it hasn't happened yet. So now there's something manipulating this experiment, and it's something with intelligence and a brain, because it's not just randomly doing stuff like a machine. It's purposefully doing things, manipulating that. It's not random at all. The system, it appears to be random, but that's how the system is able to do its magic behind the scenes. So that's what those other two experiments are like. So I do one of them like that, where the experimenter can predict whether a photon will transmit or reflect, which is just by physics just totally impossible. And then the other one, it's the let's see, it's not it's so one of them is, it's the prediction of how a particle will be emitted from a radioactive source.
All right.
You have a radioactive source, and it emits particles randomly in any direction, and then you have this big counter that detects radiation, a hemisphere on either side. And if it goes through this hemisphere, that's you're going to erase the data. If it goes through this hemisphere, you're not going to erase the which way data. So you let that change, and then it's the same thing. You look and see where the particle lands. Oh, it landed, in a place that is where a dip occurs. Then that's not part of a whatever. So then you can make a prediction. Oh, that radioactive particle, which is now 20 nanoseconds down the line, is going to decide to do, it's going to come out on the right side instead of the left side, because that makes a difference on whether you erase the which way data or don't erase the which way data.
Right.
So now it's the same thing. You do something that is just absolutely physically impossible. You can predict which side a particle is going to come out of a nucleus that's decaying, which is random. So it's impossible, and it gets you to, it's exactly the same experiment, but it's just done in a different way with a different thing. And it says, well, in order to do that, there must be something intelligent that is aware of the situation that changes what we thought was random isn't really random or doesn't have to be random. It could be random, but if the system needs it not to be random to prevent a discrepancy in the rule set, then the system will change that. So anyway, those are those two experiments, and I think they will be even more impactful than the first one. The first one, I'm afraid, is not going to end up, oh, I'm right, they're wrong, or oh, they're right, I'm wrong. It's going to end up in this thing that, well, as far as what the particles do when they leave each slit is exactly what I said they do. But the way they end up on the screen is exactly what they said would happen. So then we can have an argument about, what all that means, but it's not going to be clear. And I'm afraid that in order to measure that which way data, so far it looks like you have to throw a lot of extra variables in there. You can't just, like in my theoretical model, says, oh, you just have a detector. You just detect the which way data. You see, it's pure and easy, and it's it's no problem. It's just a theoretical thing you do. You just do it, and I think is probably never going to happen. It's always going to be complex. But now, I may be wrong there. There may be some clever scientist here someday who'll say, come up with a clever way of doing it without introducing the other issues into the experiment, like high phase changes and things like that.
Right. The SEW experiment I was mentioning it seems like it kind of does that.
Okay, I'll have to look at that. Yeah. Send me a link to that when you get a chance, Chad.
Okay. So we're almost an hour in. I got one more question I wanted to ask about the experiments, and then I want to move on. So another criticism that has been put forward is that if your experiment one worked the way that you suggested, it would allow for faster than light communication. And I at first thought that that's not correct, because people often think that entangled pairs can allow for faster than light communication, but that's not right, because you don't know ahead of time which way it's random, whether it's going to be. But I was looking at your experiment, and I was looking at it if it worked out the way you said, and it seemed like you actually would be able to have faster than light communication. You just have someone on one planet looking at the screen and seeing if it's going from interference pattern to particle pattern. And then you have someone on another planet switching the absorber on and off, and they can send Morse codes. And it looks like the person looking at the screen could get the information. It's not random, it's intentional. So what do you say about that?
Yeah, I thought about that some too. And I think I think it has two aspects to it. One, I think it does allow you to transmit data, uh, faster than light speed, transfer information. Now, information's non-physical. So you can't make anything physical go faster than light speed. That's Einstein. But information doesn't necessarily get caught in that trap, because information's not physical.
Right.
Okay? It's different. Now, you can't transfer physical data that fast, yes. But again, information is a different sort of thing. So that's a possibility. But I think it would be so totally unwieldy to make any kind of meaningful communication. If your communication can be made in 3 or 4 bits, and no more, like you got, okay, 2 ones and a 0, now what are you going to say? Well, you're just not going to say much. And it's not that easy to do these experiments. It's not that easy to set this up. And there may be some other constraints on it that we haven't thought yet. It may be some decay time on that, before the system declares that the experiment's over and it no longer works. The system's in charge. And what I mean by that is, okay, let's say you do a whole bunch of simple double slit experiments and you get outputs and you don't look at either one. You don't know what they are. So you've done them all such that there was no which way data, or you've done some of them so there's no which way data, and some of them that there was which way data. Say, so if you want, you can give somebody the screen data, and you keep the which way data, and then you erase the which way data, and now their screen data should show a interference pattern. Okay, well, the idea is that there can be an infinite amount of time between those two actions.
Mm-hmm.
I don't know that the system will allow that.
Right.
The system can make up their own, their own rules other than the rule set that it has to work with. It can just say that there's, a decay time.
Mm.
And that's not, that's only good for, I don't know, for a day, for a year, for a decade, for 10 nanoseconds, who knows? There may be some decay time that would be imposed on that, but nobody's ever looked at that or done it or seen what the other variables might be. So there may be some other, if it got to be that communicating faster than light speed was a problem somehow, then the system could do something that made that not work, like a lifetime, something that would decay. Or just the practicality of it, I think, would make it very difficult to turn it into Morse code. That would be such a cumbersome way of trying to communicate.
Yeah.
That I don't know that it would, I don't know, maybe later science that we don't understand now might make it more efficient process. But yeah, I believe it does say that you can make a communication. That depends the distance. Okay, look at that delayed eraser. When they finally, that photon gets to D1 or D2, which means it gets erased, or D3 or D4, which means it doesn't get erased, that's 10 nanoseconds later. And then the result changes because nobody's ever looked at the result. Mm-hmm. All right, so that's 10 nanoseconds. So we've done it already for 10 nanoseconds. Okay, we've communicated information. 10 seconds, 10 centimeter or 10 nanoseconds later. And the communication was, I'd say, faster than light speed. It was instantaneous. As soon as that happened, it's done. Okay, so now, if you can do it for 10 nanoseconds, you ought to be able to do it for 10 years. It's the same setup. Mm-hmm. So we've seen it with 10 nanoseconds, but we haven't seen it, for much more than that. And so I think that is a possibility, yes. But whether it ever turns out to be a practical possibility or whether the system allows it to be a practical possibility, those would be unknowns that we just don't know yet. But yeah, that's interesting that at least there's a possibility there that someday we might have faster than light speed if you could somehow harness that. But it's not exactly a kind of technology that you can imagine that it would be. It would be really hard to get enough bits there that you could have anything more than a grunt and a gesture. It'd be very, very simple communications.
At least for now, yeah.
Yeah, at least for now.
Okay. All right. I want to move into epistemology. So you sent me some definitions. These definitions, I think, are also on your website. When you define awareness, you include awareness as knowledge. And so I'm interested in defining knowledge and belief. And I'll just read what your definition says. Awareness as perception requires data as an input. Awareness's processing and interpretation of this data describes that of which awareness is aware. Awareness as knowledge requires memory, or every instant would appear to be the first, and some very rudimentary processing, since perception is eventually processed into knowledge through the interpretation of data. Knowledge represents information and is a property of consciousness. I've got some more things here. An IUOC contains an ever-changing knowledge and experience base of information called its content. So with regard to epistemology, right now, there's kind of two major camps with thinking about knowledge. One is still kind of all the way from Plato, I think, the idea of defining knowledge in terms of belief. And knowledge is a justified true belief of some sort, which is interesting because in your epistemology from your book, it seems like, obviously you would not define knowledge as belief because belief is sort of an impediment to knowledge. And I was kind of wondering what your take on what knowledge is you're defining consciousness as awareness with a choice, and you're saying you can define awareness as knowledge when you incorporate memory. So I just wonder if you could talk a little bit about.
Okay, sure. Where Plato went wrong there is that he was assuming that there were such things as known correct beliefs. If his idea was that if you had a belief and you knew that that was correct, then that was knowledge. You never know if it's correct, is my point, or you very seldom know if it's correct. That's a rarity. There's always uncertainty about whether something is true or not, unless you do very simple things. If we limit it just to trivial things, do I have two rocks in my hand or do I have one rock in my hand? Well, you can look at that and say, oh, 1, 2, there's two rocks. So two rocks in your hand is true. So if you're going to limit it to simple things like that, then yes, you could kind of let Plato's definition stand. But if you want to talk about knowledge beyond the trivial, then you can't do that because you don't know whether things are true. If somebody, gives you some kind of statement about reality, if somebody says, the moon is made of green cheese, okay, now someone may believe that. And to them, that's true because that's what they believe is true. And that's their truth. That's their knowledge. Okay, so, but that's not true to other people who would disagree with that. They say, no, it's made out of rocks and a lot of sand and rocks and other debris, like one would expect. And they have their reasons, and that's also their truth. Okay, now, each one feels that they have knowledge. Is it possible that they're both wrong? Yes, because in my viewpoint, there is no moon. The moon is a calculation, and it appears as if it has dirt, as everything in a virtual reality appears to be the way it is. It appears to be solid. It appears to be a rock. It appears to have dirt. It does not appear to be green cheese. But what really is it? It's a calculation. It's just information. It's not dirt. So it depends on the lens at which you look through things, the foundation upon how you've decided, reality is. So if you're a materialist, it's rocks and dirt, and that's a fact. If you're not a materialist, if you're, in the MBT camp, then no, it's not really rocks and dirt. That's just as if it were rocks and dirt. It acts as if it were. It's a calculation. That's the nature of our reality. And if you were a peasant in the 1500s, green cheese would maybe sound pretty close because that's what it looked like. That's what that kind of cheese looks like. It has kind of holes and dimples in it, and about the same color. And who knows where that that green cheese came from? But in any case, we can imagine that maybe some people did think that that was the way it was. But I just made that up. That's just whether anybody actually believed that or not. It's not the point. The point is that it depends on your viewpoint about the nature of reality as to what things are. What are the facts? So at this level, you've got some simple folktale. And the next level, you have, a lander that landed there, dug up some samples and flew home. But on the next level, all of that's just information. There is no dirt. There are no particles. So what's true? And how do we define truth? So what I do, what's different about me than about anybody else who talks about knowledge, my epistemology is different because of two things. One, awareness that produces knowledge, I don't restrict that just to the physical. So the physical reality is not, the source of all knowledge. There's knowledge can come from other places, but I suspect other philosophers would agree with me there. You can derive knowledge from thinking about things. But knowledge is always uncertain. My personal knowledge contains all the uncertain potential facts I'm aware of through my experience, which are assessed in terms of probability of being true and the probability of being useful to me. So those two things. I have things that I'd say are facts to me, but does that mean that I'm saying that never will knowledge or any information ever come about in the future that would show me wrong? Like to show me that the dirt really wasn't dirt, it was a calculation. You see, you don't know what information may become available in the future. So you have to keep your knowledge as potential knowledge. And you have to say, well, I think that, this is the way reality is. And I'll think that to 0.9 or even 0.99999 if I'm pretty clear about it, or maybe even 0.9999999 if I really think that that has to be it. But it's very unusual that you ever say it's a 1 or it's a 0, because there may be information that shows you that it's different than the way you think it is. You don't know everything. So it starts with the premise is that we don't know everything. We don't necessarily know the nature of our reality. And because of that, we have to look at knowledge as potential knowledge, uncertain knowledge. And as you have experiences, they should lead you to change those probabilities. So here I am, and I've got all these things that I've experienced. And to me, these are the things of my truth, things that I've done. And I've made up little stories about why they're like that. Oh, the moon's made out of rocks because we went up and, I didn't do that firsthand. I wasn't there. I didn't see the rocks, but somebody went up there and got rocks and brought them back. And I've seen pictures. And I believe that that's true because it seemed very improbable that it wasn't true to me. Okay, so that's my truth. So I say I'll put the fact that they look like rocks, they appear to be rocks, is a very high probability. But I would also say they're not really rocks. They just appear to be rocks. It's just information. They're not actually, there are no rocks. There are no particles. So I have that as a high probability. And let's say the probability that, oh, that moon landing never took place. That was all, that was all faked. Well, I'll put that at maybe 2% or 5%. It's possible. I mean, it's not impossible to put one over on me. I'm not the smartest person in the world. I don't know everything. I wasn't there. I wasn't a part of it. I just read about it. And There's lots of things that go out as being facts that really are just wrong. There's a lot of wrongness that is believed. So would I say that it was faked is zero probability? No, but I don't put it very high. I'd put it at maybe a 2 or a 3. Point 0.1, 0.2, maybe even 0.001. I would put it as a small possibility, but because I wasn't personally involved, it isn't part of my experience. It's second and third and fourth hand that I got from, the people at NASA who told it to reporters, who told it to, their various papers. And finally it got to me in articles and things like that. So, you never, unless you're personally involved, you don't know what the real story is. But because I trust that we actually did send one there, I have a pretty high trust level that we did have a mission there, and they did come back with rocks and dirt from the moon. I give that a high probability. But that's just me. There's other people walking around that give that a low probability. And for me to say, well, they're idiots, they're wrong, well, that's not a good thing for me to say. That's very judgmental. All I can say is that this is the way I have come to think about it, and realize that everything that you have really boils down to belief, yes, but not beliefs that you believe are true. You believe that this is 0.999 likely to be true, not that it is true or that it is false. So that's the thing about my epistemology that's very different. My potential knowledge, which is all my knowledge, is potential. My potential knowledge contains all the possible uncertain potential facts I could be aware of through my own personal experience. And all of those potential facts are assessed in terms of probability of being true and the probability of being useful to me. See, that's another thing that I add in. If it's a fact about, I don't know, things that really I don't care about, aren't useful to me, then I don't care really how right or wrong they are. So I don't take a lot of time thinking about it and giving them a probability, because it just doesn't affect, I don't see the interaction potential in my life. Now, I may be wrong. Some of those things that I put in that basket may actually turn out to be important. Well, then I have to go collect it. I have to take them out of that basket and put them in my basket of things that I pay attention to, that I carefully give them probabilities based on, what I think is likely to be true. And everybody has to do that for themselves. There's no way that you can have, let's have this commission of all the very smart people, and they will tell us what to believe. Nonsense. That doesn't work. They don't know everything either. They're just also assorting according to their experience and their probabilities. No, thank you. I'd rather sort my own and give my own probabilities out. So everybody has to, there isn't anything out there that this is the truth. The truth doesn't exist like that. Reality isn't a machine. Reality isn't material where things just are the way they are. Either it happened or it didn't. Reality is probability. Reality didn't either happen or it didn't. Now, we do have a history thread, but there's a whole lot of people that read that history in different ways. They see it differently. So what we have to do, my epistemology says we have to learn to live gracefully with uncertainty. There will be many things in our life that we will not know whether they're true or not. And what we have to do is, one, make an assessment. How important that is to me, knowing that particular thing. And if I think it's significant or important, then I need to spend some time researching it, learning about it, discussing it, and then come to some kind of opinion to where I'll put its probability. I put that probability at 50-50, because when I researched it, I've found as much stuff that says that was true as I did find stuff that says that was false. Now, maybe that's because that thing happened 100 years ago. And what's written about it now, there really is no way you can tell for sure. But let's say it just happened yesterday. Well, now I can do a lot more research, a lot better. I can find people who were there and talk to them if I want to go that far. Or I can say, well, it doesn't mean that much to me, so I'm not going to try to find people who were there to talk to them. I have these sources, and I generally think these sources are accurate. But I'll never say that they're so accurate that I'll always give them a 1, that what they say is absolute truth. They're not that accurate. So that's the way I deal with knowledge. You have to realize that knowledge is uncertain. The idea that, there are these beliefs that are true is somebody who has an idea that this is a physical reality where things are true or not true. And that's, fact or not a fact. It's either truth or it's an opinion, but it's not like that. Reality is probabilistic, and knowledge is also based in probability, and one must learn to live gracefully with uncertainty, because you'll never know whether the things you think are facts are really facts or not. Now, I've got a whole lot of things that I keep at 0.999. I find I think, to me, those are the things I treat as very likely to be facts. So I make my choices based on those things very likely being facts. But I won't say that they're one probability. They are certain, because I don't claim to have all knowledge, particularly knowledge that we'll find out in the future. You see,
Okay.
so that's my view. That's my viewpoint of knowledge and epistemology that kind of makes me very different than other philosophers.
So you also say that in your definition somewhere, I found this quote: belief meets a need for certainty where no certainty exists.
Mhm.
So, so how do you, so you've just described how you deal with knowledge. So would you be saying then that what belief is like putting something at a 1 or a 0?
Yeah, I'd
Clearly?
say that's probably a good way of saying it. It's not just any something, but um, putting many things, or putting complex things that are outside your own personal experience. And even your own personal experience, you can't always believe your eyes. You can't always believe your ears. There's people out there that can show you things and you'd swear that it was like this. That's what you saw, and it's not what I swear this guy had that saw and sawed that lady in half. I watched that lady get in there, and I saw her in half, but there wasn't any blood, and at the end she came back whole. So now I know that it wasn't as it seemed to be, but I have no idea how he did that or how that was arranged. You see, I'm ignorant of that process. But so there's even the things that you witness yourself. Again, a lot of those are going to be 0.9s and 0.999s, but even some of those may be the fact that you interpret it wrong. There's things you don't know. There's hidden variables. There's other stuff that you're ignorant of that would make it different than the way it seems. So even the stuff that's your personal information is also uncertain. It needs to be uncertain because you just don't know everything. If you knew everything, then you could tell whether it was a fact or not. But given that you're not omniscient, then I think your humility requires that you realize you don't know everything, and you could be wrong about a lot of things. And that woman being sawed in half would be one of them. There's stuff that looks one way and it's not really that way at all. There's all kinds of people trying to get us to see things their way, influence the way we see reality. And most of them have agendas that are not discussed. And even personal people have agendas. They just want people to agree with them. So they just, enlarge the story. The fish was really this big. The story gets bigger because they'd like people to think that they caught this really big fish. Well, did they or not? you have to say, well, that's George. I know George. George generally tells the truth, but I really don't know how big that fish was, but it doesn't matter how big the fish was. You see, now you come to that. So it's not important knowledge. It's not something I need to know. So it's not important to me. If George caught a fish that was, 3 feet long, or caught one that was only, 2 feet long, or even 2 inches long, doesn't make any difference to me. So I put that in, don't really need to know. I'll just let that one ride as irrelevant. So I will accept his story that it was 3 feet long. And, if I repeat the story, I'll tell George caught a fish that was 3 feet long. I will just take it at value, or I'll say George says he caught a fish that was 3 feet long would be more accurate. So that's how you deal with that. So, pseudo knowledge, what I call pseudo knowledge in my book, is where you've given something a 1 or a 0 when you really don't know whether it's a 1 or 0. You don't have that kind of information, but you've done it anyway. Mm-hmm. And there's a lot of that going around. That people have a fear of not knowing. They have a fear of uncertainty. They don't like to be uncertain. They like to feel like they know the answer. So what they do to get that uncomfortable uncertainty taken care of, to get rid of that, they just make stuff up. They turn things into what they would like it to be, and then they pretend that that's the way it is. Now the uncertainty's gone. They have a belief, and that's that. They're believers. So I think that belief produces pseudo knowledge.
And that cuts you off from this. I think you say somewhere it shrinks your solution space. It cuts you off from other answers, right?
Yes, that's the problem with belief. Belief, if you believe this is true, then you no longer are looking for data to show you that it's not true. If some data comes along and says, "Oh, that's not true," you go, that's bad data. That person doesn't know what they're talking about. They must be an idiot." So you automatically throw everything away that disagrees with your beliefs. That's, people do that. Rather than walk around with uncertainty, they'd rather walk around with a belief and feel certain that they know. That's a fear. And that's one of the ways that fear affects our life. So yes, the problem with belief is once you got a 1 and a 0, you no longer are making reevaluations and sliding that thing from a 0.9 to a 0.6 to a 0.5 to a 0.3, because you're learning more and more about that. You're not able to shift and see things. Here's a good example of belief. I went to a course where a lady taught seeing without eyes. And what that means is they put a blindfold across you, a big blindfold that goes from ear to ear, and it's about that wide. It really keeps you from seeing. So the idea was to teach us to be able to read, to be able to see each other, to be able to see anything that was out there with this mask on. So what we were doing was remote viewing in real time.
Right.
That's what it amounted to. You just remote viewing what was in front of you, what would be there, what letters were on the page, in this book, and you learn how to do that. Now, she found that she could teach 5-year-olds in an hour to do this. And 5-year-olds that were particularly troublesome in less than a day, but some of them she could teach in an hour. She could teach 6 and 7-year-olds in a day. She could treat 8-year-olds in 3 or 4 days. Adults, if you could teach them at all, took at least 2 or 3 weeks, a month. Now, why is that? Why are the children so much more adaptable? Because they have fewer beliefs. Because when they think, I got this mask on, I can't see. It's impossible for me to read a book when I have a mask on, it just can't happen. And that belief actually inhibits you from being able to do it, because you can never, every time something happens where you get something, you throw it away as wrong, a hallucination, a trick. The way that she taught it, the main key idea that she had in teaching this was basically, how do you get people to let go of their beliefs? Because if you could do that, if they didn't already have their mind set up that if you don't get light in your eyes from something, then you can't see it. If they didn't believe that, then in an hour you could teach them to, you know, read a book with their eyes shut, or in a room that's perfectly black, all the doors, windows, everything closed and sealed off. They could read the book. Well, now they could remote view other things too. They could remote view what's on the other side of the, dark side of the moon just as well. They could get any kind of knowledge. They're just getting data from the database. So, and you could do it in real time. And most remote viewers don't have any idea that they could do that in real time, because it's such an effort for them just to do it in one spot. But you can learn that in real time. So anyway, that's an example of how belief locks you into things and makes it very, very difficult for you to gain information that is contrary to your belief. So it traps you. I call it a belief trap. You get trapped, and now there's a certain part of the world that you no longer can understand, or you just can't go there, because your mind will refuse information contrary to what you believe. And that gives us certainty that we're right. Oh, I'm certain that I'm right. I'm certain that all the things I think are true. And that gets rid of the fear. It doesn't really get rid of the fear, but it kind of whitewashes the fear, so the fear doesn't bother us.
Okay,
So that's what's going on.
great. That's helpful. So we'll move to the next topic. I think this might be a shorter topic, but something that I found very interesting in your work is you treating so the concept of infinity. I think it's really an attractive concept for philosophers in particular. It seems like it's got a lot of explanatory power, and it seems like you can explain strange things using it, and the philosophers tend to like paradoxes. But you say nothing real is infinite, and for me, it kind of clicked. Something clicked when you said that, and it makes, like, so we're dipping into metaphysics now. So to me, it makes metaphysics more real in a way. It makes things more logical and rational and just real if you go with the idea that, okay, so nothing real is infinite. This also kind of bleeds into your concept of using a theory of time. Time is linear. Everything's not happening all at once. So to me, um, and it also has something to do with, in religions, they often think of God as perfect or omnipotent. It could do anything.
Right.
The concept of the larger consciousness system is it's finite, it's imperfect, and it's evolving, um, which I also find makes it, to me, more of a real thing.
Right.
I wonder if you could just talk about that a little bit.
Yeah. Well, it's really a simple idea, and that, in mathematics, infinity is a place you can never get to, right? You can only approach infinity, but you can never get there, because if you ever got there, you could always add one to it, then you'd have something bigger. Well, that would be impossible, because uh, infinity is as big as it can get. You could always take whatever number you thought infinity was and you could square it, multiply times itself or raise it to the 10th power. So there is no infinity that you can get to, as long as, if you're talking about something real, something that is like consciousness is real. A brick is a virtual reality, but within that virtual reality, you've got rule set, and within that rule set, you don't have infinities either. You can't have an infinitely long brick. It's just impossible, because you can always stick another little more bits of brick material on the end of it. If somebody ever got to the point and said, okay, you finally made it, that's infinite. Oh, you could just stick another little piece onto the end of it. Now you'd have something bigger than infinite, which is impossible. That's the definition of infinite. Infinite is there's nothing can be bigger than infinite. So infinite just keeps growing to the point that infinite isn't defined. You see, infinite is not a real thing. It's an idea. It's a concept. It's something we can think about, and in the sense that we move toward it but can never get there. So it's a thing you can approach, but you can't get there. And that is the way you get infinity in mathematics. As this approaches infinity, that value goes to such and such, because you've got you've got some sort of thing that gets smaller and smaller and smaller and smaller. So as you go to infinity, it equals zero. That sort of idea. So that's the way mathematics takes it, and that always seemed to me to be rational. Now, when you talk about things that are really big, we use infinity as a metaphor. Oh, I'm one of my favorite metaphor or analogies there is, you're sitting in an inner tube in the middle of the Atlantic Ocean, and every direction it looks the same. Water, waves, water everywhere. And you've been there for a month floating around in this inner tube, and the view in every direction stays the same. You might think that you were in an infinite sea of water, because from your viewpoint, it is infinite. You cannot find anything else in any direction, no matter how hard you go or how much you paddle or how fast your engine is or whatever. You just can't. But you see, it only appears infinite. If you really had a fast engine, in a week or two, you could find land. Or if you could just live there long enough to where the currents took you someplace, you'd find land. It's not really infinite. It just appears to be that way. Well, anything real has to be finite. It cannot be infinite, because an infinite is impossible. Anything infinite is impossible just by the definition of infinite. So that's, I guess I was kind of biased to that viewpoint because I came up through mathematics. And in mathematics, that's obvious. That you don't get a number that's infinite, because you can always square it if you want to, whatever that number is. You never get to infinity. It can't exist, just a concept. So because I came up through math like that, then it was easy for me to see that applies to everything. Infinite isn't a place, isn't a real thing. It makes a good metaphor when something's really, really big. Then we can say, oh, it's infinite, but it's not true. That's not a fact. That's an exaggeration to make a point that it's really, really big. That's we say that all the time. Like let's say we have 9 billion people here on the planet, and all the possible interactions of those 9 billion people are infinite. We just say that because how many different ways can 9 billion people interact with each other? Well, each one could interact by probably 10,000 different ways. So you could do the math, but it's not infinite. That's the problem. It's not infinite, but we say that because it's really so big that we can't imagine it. We can't think about it. We can't compute it. So we say it's infinite, but that's just a metaphor. It's not math. It's not a fact. It's just an exaggeration or hyperbole that we use to make a point of it's beyond our ability to deal with it or to
Okay.
think about it.
So this kind of bleeds into my final topic here. So when talking about space-time, so there's, I think it's generally thought among physicists today. Obviously, there's a few that disagree that, and I think Einstein, his relativity theory is based on the idea that space-time is continuous. Obviously, if we live in a virtual reality, it's discrete. Um, and you've pointed out that the speed of light is sort of derived from space-time being discrete, because if you go 1 pixel of space per 1 pixel of time, you get the speed of light. Um, so you run into Zeno's paradoxes and stuff when you think about continuous space-time. Uh, I wonder, how do physicists deal with that? I mean, you have quantum physics, which is mostly discrete stuff, and then you've got relativity theory, which is based on continuous space-time. There's a conflict between the two.
Yes, there is.
Do you think that that's kind of fundamental to that incompatibility between the two?
Yeah, that's one of the incompatibilities. There's another incompatibility between quantum physics and relativity. Um, in that, well, let's see. I shouldn't say it because I can't really get it right, but there is another uh, incompatibility there where it's the way they use space and time. It's like in relativity, you have kind of an absolute continuous space, and anyway, and in the other one in quantum physics, you have like a continuous time, but space is in chunks according to probability. So it's like there's this difference between them that is yeah, very much what you were talking about. But they have a fundamental philosophical disagreement, and the way I've heard it said is each one has a fundamental thing that they believe that the other one says is not true. You know,
Right.
one believes X, the other believes Y, and the one that believes X says Y is not true, and the one that believes Y claims that X is not true. They have that dichotomy, which was the reason that they knew that there was something more fundamental above both of them. Neither one of them can be the answer because they both just work in their own subsets. They don't work everywhere. They are partial knowledge because of this disagreement they have, and that's why they were looking for the theory of everything, because they knew that those two worked well in their own regions, but there was things about them that were that were conflicted with each other. That means there was something else above them that was whole, and these were just two piece parts. That was the idea. So that's what told them that there was a theory of everything, and that's what they were looking for, so they could find that overarching idea that would explain both relativity and quantum physics. And they'd now both be piece parts of something bigger. So the piece parts are allowed to be different. They're allowed to conflict with each other. That's okay. They're just piece parts. But the thing that's fundamental has to be whole across everything. So that was why scientists have been looking for this theory of everything, ever since. That they're convinced there is such a thing. And of course, that this is a virtual reality computed by consciousness is exactly that understanding. It says, here's relativity, here's why C is a constant, and it says that here's quantum physics. It's because our reality is fundamentally probable. It's a computed by probability. It's a probabilistic virtual reality.
Right.
And it explains both of those. And when you talk about relativity and its concept of curved space-time, and yes, it's continuous. Well, physicists basically, well, I shouldn't say, I don't know how many, but a large portion of them, I don't know whether it's a minority or a majority, believe that reality is continuous
Right.
because that's what they see.
Right.
They don't see the pixels. Okay, they know that their television set, has pixels. They can see that, and if they get a big magnifying glass out, they can actually, see each individual pixel. They back away from it, and they can't see the pixels, but they know they're there. But reality, they haven't actually looked at the pixels yet. Now, quantum physics says that the Planck length, Planck time are about where the pixels would be. That's kind of the smallest length and smallest time. It appears that way from what they understand about quantum physics. Okay, it appears that way. So that's what I use. I use Planck length as delta x, Planck time as delta t. But now those are very, very small. They would say that reality has a very extremely high resolution because that's really, really tiny pixels. So it has a very high resolution. Computing anything at real high resolution takes a lot of computation. There's a lot of data is involved. So the smaller your delta x and delta t, the more crunching you have to do to do anything. So obviously this virtual reality I'm talking about doesn't use any more resolution than it needs to, doesn't compute to any higher resolution than it needs to. So you go back, even just 200 years, and probably, what, a couple of fractions of a millimeter was about as much resolution as anybody ever got to, and then they had magnifying glasses, and okay, maybe 100th of a millimeter was as close as anybody got to. So you didn't need a lot of resolution to model the world a few hundred years ago. I guess you could see your resolution was about as much as you could see. And people were surprised when they got microscopes and things like that, and they could see all this little structure going on, and that they never knew was there. Well, now the reality had to be modeled at a level of that structure because they had the tools that could see it. So suddenly, the rendering engine had to develop at least portions, those portions where people were using microscopes. They'd have to render that at a higher, resolution to show them what was seen in the microscope. But when they weren't looking through the microscopes, they didn't. So that added just a little bit of extra calculation. So it's not true that the system, once they had microscopes, had to render everything at, what, a thousandth, of a millimeter or something like that. They didn't have to. They only rendered what they had to for as long as they had to. And that's the way it generally goes.
So when the speed of light, um, forgot the name of the person who said that the speed of light changed a little bit in the
Yeah.
time we were figuring out quantum mechanics. It seems like that would only be necessary if they had to change the entire resolution.
Yeah.
Uh,
Well, they had to change the resolution to the physicists who were measuring the speed of light,
okay, okay,
because those physicists were also measuring other very small things,
gotcha.
and they had to do that. So they have to keep it consistent.
Okay,
So they don't have to they don't have to render reality to the plumbers that way. Plumbers don't ever get into things that small. Dirt under their fingernail, I guess, is as small as they get. So it can be
so
rendered. Each individual gets a data stream, and the resolution in that data stream is what that individual demands. Now, if they have very fancy equipment for measuring the speed of light, then they'll get a speed of light. And if they can measure other things, well, that speed of light's kind of central to a lot of what goes on here. It's one of the basic things, how fast things can travel here. So if we get to the point where we can measure it more accurately, then they need to give us that. And if there's some fundamental things that we will find out later require a speed of light to higher accuracy, then it needs to give us that too. So yes, we have seen the speed of light change a few times, and it's not measurement error. It's at a level that it's inside of the what we would call the plus or minus measurement error. It's small. It's bigger than that. So we know that it's real, but we don't really know why. I mean, there could be several reasons. One, for some reason we need, or those people who were doing the measurement needed to see that extra resolution, so it's gotten better. Or it could be the other way. It could be that they don't need that much resolution anymore, so it could be moved back so that the calculations don't take as much throughput, as much data. It could be either way that it's going. It's not, sometimes it shrinks a little, sometimes it gains a little. But the reason for that is whatever the change is, it can't be exactly the same unless it stays exactly the way it was, because it's digital and you can't shift things to make them come out to 50 decimal places to be just right, or 1,000 decimal places to be just right. You have to shift them by a whole, pixel one way or another. So they're going to shift a little bit when you do that. So if you looked at that, where was that thing? Let's say it was in the 8th decimal place at the speed of light is where the change was. Then that tells you that that's about where the computation is being placed. Our virtual reality is being computed to about the 8th decimal place. And other than that, we don't need it. In our daily lives, more than 8 decimal places is redundant or not useful. We don't live lives that get into those kinds of details, so that's where it's mainly computed. And then if it shifts a little bit this way or that, maybe it's gotten a little different. It's been moved up, it's been moved down. I don't know exactly what those reasons are, but it could be that we in general are looking at smaller things, more of us, more often.
So in your books, you mentioned Stephen Kaufman's book, Unified Reality Theory, and you
Mm-hmm.
kind of present this as an attempt to kind of work out the details of how a virtual reality would work. And you
And to
said,
work it out graphically, basically like Einstein did. Einstein is what is the right way to say it? Geometry.
geometry.
He kind of uses geometry to develop his theory of reality. Einstein used a geometric solution to gravity. Space is curved.
Mhm.
That's a geometry. It's the curvature of something. I guess people call that topography, but that's surface curvatures and so on. But it's geometry based, and that Kaufman, yeah, I thought it was interesting because he came to a lot of interesting conclusions with his geometric models that he was using, and I thought that to me that showed that there's multiple models that can give you right answers. Okay, well, for instance, gravitation, G equals mm over proportionality constant G, which they call G, the gravitational proportionality constant, times the mass 1 times mass 2 divided by the distance between the centers squared. All right, that was Newton's formula for the force of gravity. And Now, Einstein says, oh, it's curvature in space-time. That's what's doing it. Two different models.
Mhm.
They both give you the same answers, more or less, for many things. But Einstein's is a little broader. It gives you more answers over a wider range because of the relativistic effects. If you're talking about far enough away and fast enough speeds and all that kind of stuff, then the relativistic effects of that curvature are shown, whereas m1, m2 over r square has no relativistic effects in it at all. It doesn't add those kinds of things. So then that makes Einstein's a little more general of a model. But they're just two different models. And to think that space-time is really real, is a real thing. Oh, we live in a space and the space is curved. And that's why, a bowling ball and a trampoline, they all tell you that thing, well, everything rolls toward, that's the force of attraction between masses is because of this curved space-time. And that is just a model. That is not a truth. You see, the problem is that physicists take models and then they believe them. They believe that they are facts. They're not facts. It's just a model, and there's somebody else will come up with a different model, and he'll be able to get the same answers, but it'll be a different model. So I look at space-time as the best model we have right now, because it includes things in large scale and high speeds, whereas Newton's didn't. So it's a more general model, but in most cases, if you just want to compute gravity so that you can launch a spaceship so it goes out and uses the moon for, a little extra push, and a little extra pull, then fine, you can do that with Newton. You don't need curved Earth to do that. You can do most all of that simple stuff because rockets don't move anywhere near the speed of light, so there's very little error. So all of the satellites and all that stuff, they don't have to correct, for relativistic effects. So they're not going that fast. So Newton's just fine for all of the basic stuff that we do that deals with gravity. It's just a different model, but his model is limited, whereas Einstein's model does the same thing Newton does, but it's a lot more complicated. And the complication buys you the extra sensitivity to high speeds, long distances. So that's the difference. But no, we don't live in a space that's curved space-time. There is no space. It's just information. It appears as if there were space. It appears as if you had a brain. It appears as, if this is a physical world, because that's the rule set, makes it look like a physical world, but it's just information. So the reason that GMM over R square computes forces between masses is because that's in the rule set. Gravity is a part of the rule set. Because you need gravity. If you didn't have gravity, then nothing would stick together. If you're going to make stuff, if you're going to make massy things, then you need something to hold them together so they all don't float off into never land. So gravity is just a necessary component. So it's obviously one of those rules in the rule set that helps everything stay together. And you can't have too much because everything would go slam into a big ball, and you can't have too little or it'll all run away. So you have to have just the right amount of gravity. So you find out that coefficient for the G coefficient for it's just a proportionality constant. It's proportional to the product of the masses divided by the square of the distance between the masses. And then G is just a proportionality constant, which you get by making a measurement. And you come up with that. Well, they measure that to, I don't know, like 8, 10, 12 decimal places. It's not just any old constant. It's obviously very carefully and precisely picked so that this reality can be stable. This virtual reality, we call the physical universe, can be a stable place. It's important that you get it just so. So
So
that's, so yeah, I don't, space-time is not a fact. Space-time is just a model,
right.
as if, and it's the same thing with particles. An electron is not a fact. An electron is a model. What we see are things that we measure as if there was a particle with a charge. So we look at the data that we see and we say, okay, that data is as if there was a particle with a charge. So then we make up a model. We say, well, let's call it an electron. It'll be a mass with a charge. So we make that up, not because we've ever measured an electron. We've never seen an electron. We've never measured an electron. We see the data that electrons leave when they interact with certain things. And it's as if there was this little point with charge and this little mass with charge. So anyway, all of our physics is like that. It's not that these things actually exist. They're models. We make up a story. So the electron's the story we make up in order to explain the data that we take. But it's just theory. An electron is a theory of the electron, if you like, or as if there was an electron. I just like to say as if. And physics does this with all of its stuff. So we look at gravitation, as if space-time were curved. It doesn't mean space-time's curved and that the space you live in is really curving all around you, and wherever you walk, little curves of space-time do this and that. But physicists forget that they make all this stuff up as a model of how things work. All the physicists get is the data. They collect the data. They try to make sense of the data, and they make up a model that will give them that answer, as if electron existed, as if you had atoms that were like this, as if, quarks were there and they, made charges. And, all of this is, we look at information. Okay. We don't measure things at the 10 to the minus 15 level, very well. We measure the things we can measure, and then we make inferences, the as if, as to what causes it. All of physics is done that way. All of the particles were done that way. Space-time is done that way. It's all an inference from what we can measure. We infer that it must be that way, because if it was, that would give us this answer. Well, that's not necessarily complete. You can have many models that'll give you an answer. You have Newton's model, that gave you an answer. And then you have Einstein's model, and that gave you an answer. And you have Steve Kaufman's model, and that gave you an answer. So it just shows you that there's lots of ways that you can get answers to explain the data, not just one way. So how do we deal with that? The way a physicist should deal with that is that you don't believe any of it. All of it is just models.
Right.
Theory. That's the way you deal with it. You don't make it facts. You make it ideas. These are concepts. And concepts are subject to change. And no, we don't necessarily have electrons. We have points with the attributes of mass and the attributes of charge. That's what we have. Well, that's how you model an electron in a computer. It's a point with those attributes. And they're finding that that is a much better model than a piece of charge, a piece of mass with a charge. So in any case, all of physics is that way. But the problem is that physicists, after a while, they start to believe in these models as real physical things. It's like that. And that's not so. It's not like that. These things don't exist. They're calculations. There is a rule set that produces results like that. because the computer in consciousness, one of the first things it did was explore mathematics. I mean, that's the most trivial thing at all, Well, I got a 1 and a 0 and another 1 and another 0. How many do I have altogether? How many ones do I have? How many zeros do I have? It's just basically looking at quantity is like the most trivial thing you could do when you're just playing with ones and zeros, this way, that way. Binary just kind of leads you into quantity. Quantity, mathematics is the logic of quantity. Well, everything almost in our material world is in terms of quantity. The mass, the temperature, the size, all of that it's all quantity. So then we wonder, gee, how does mathematics describe our world so well? What an amazing thing that mathematics would describe the world. Well, it's not amazing at all. The rule sets are very mathematical. The computations are mathematical because our reality is based on quantity, and that's what math does. It's the logic of quantity. So I'm not sure exactly where this is taking us, but my point here is that don't take these things like space-time too seriously, or electrons, or any of the rest of it. These are all models that somebody made up to explain measurements. None of this stuff has ever been measured, but we remeasure the effects that we get, and then we make up a model to explain them. It's a mistake to take that model as a fact rather than as a model subject to change. So there's lots of ways. Just because Einstein comes up with his model and it works with what we know now doesn't mean there won't be another model that doesn't have anything to do with stretchy space-time that'll be made up later that'll even be better. Well, there goes stretchy space-time. It lasted for a while, just like GMM over R square, and then it gets replaced by something else. So we have to have the bigger picture and not be, again, it's the same thing. People don't like uncertainty. They want to believe that they understand what reality is like. So they tend to come up with beliefs in the way things are. And most physicists will tell you that space-time is a real, that's just the way space is. It's the nature of space. Now, the way you make space in a virtual reality is you define an origin. You say, see this point? That's the origin. Now you define 3 mutually orthogonal unit vectors. At that point, bingo, you've got space in mathematics all the way from plus infinity to minus infinity, in 3 dimensions. That's how you make space.
And do you think
that defines space in a computer? So this idea that space is stretchy, this and that, it's as if it were that way, because that is a model that describes the nature that we see in gravity. But that's not really the nature of space. It's really just mathematical. It's a 3-dimensional set of unit vectors that define every point in space forever in a 3-dimensional space.
Right, but you're also saying that it's not continuous. So you're dividing space into smallest units.
Right.
And one thing that Stephen Kaufman proposed is that, there's the question, if space-time is discrete, what are the pixels? Are they squares, like pixels on a screen, or what are they? And he proposes that the best way to model it, that's maybe not exactly what they are, but the best way to model it is cubic close packing of spheres. So the smallest units of space would be like spherical volumes in this specific cubic close packing arrangement. So is that something you would like as far as models go? Like, obviously it's just a model, but maybe a better model or a way to model discrete space. Would that
Yeah,
be something?
it's like how does the larger conscious system compute? What are its how does it compute things? If you were computing a model, if you made a model of something, maybe it was just a model of an airplane, flying through the sky, you'd have to have some delta t that went around and some equations about the flight path and gravity and wind speed, and you'd have all these things that would be in there, and you'd work through that by every delta t you'd change the new you'd compute the new position of the airplane. Another delta t, where's the new position of the airplane? And if you did that with small enough steps, then anybody watching that model would see a smooth flight of an airplane, right? So that's the way that works. Now, when you do that, are you using spheres or are you using cubes or what are you using? You see, what's the difference? Well, you're just using distances. You're just computing distances to all these various places. You don't really care about, the geometry of the pixels really doesn't exist. You have a delta t and a delta x, and that's the smallest thing that you can move. So you have a delta x. Now what he's looking at is, okay, there's a delta x. Now is that a delta x in a little cube, with three little delta x's making a little delta x cube? Or is that a little sphere, with a radius of delta x, or a diameter of little delta x? You could make up any kind of thing you want. And I don't know really what difference that would make, because when you compute things, you compute distances.
Hmm.
You don't count pixels.
Okay.
You don't count, say, oh, this is so many pixels over and so many pixels up.
Okay.
Basically, you compute a distance to a thing. And if that happens to land on the edge of a pixel or the middle of a pixel or wherever you are, this pixel or the one next to it, then that's the distance. So I'm not sure how important it is how you pack them, but I think that I'm trying to remember. I read that such a long time ago that I think that he had some pretty good arguments for why the spherical was a little neater space to dealing with it
Yeah.
than if you were doing computations and you felt like you had to break it up into pieces, that the spheres would be a little neater way to do it, because the linear stuff that you get in a little cube is just more work.
Right.
You've got a radius now that'll point in any direction, it's the same length. Instead of a cube, you point in any direction. You got to compute the length every time you change the direction.
Right.
So just in a computational way, I'd say yes, there's probably a smarter way to do that. But I would say that nobody ever needs to do that.
Okay.
Nobody, nobody ever. You compute distances between things, distances, whatever, and here's the distance between this and that, and it's so many. You can fit that into so many pixels. It's like the pixels are in your display screen,
Hmm.
right? Pixels aren't necessary to your reality. It's not that we're in a sea of pixels. Pixels are just the way it's displayed on your computer. And your pixels have to be such that if you put dots of color, dots of light in the pixels, and you want them all to mesh together, all those dots of light need to come together to show you a picture. Well, you need that for pixels. But the world itself doesn't have to have little geometric shapes as pixels. All you need to do is compute distances. Now you can only compute it to the nearest delta x, and you can only compute it, every delta t. So those are your limits.
Okay.
So if you want it to come right here, and you're here, and the next delta x is over there, well, too bad. You're not going to get it here. You're going to have to be here or here. You're not going to get that little distance right there because you're going to jump over it. You can only get so close to it. And maybe here was as close as you could get, because when you jumped, you'd be farther away from it on the other side. But you're just going to compute a distance someplace. And you can compute that distance to, as many decimal places as you want until you get to a point where it doesn't make any sense anymore to have more decimal places.
Okay.
Right? You can say, here's a distance. Now I can compute that distance to 300 decimal places, but once I get to about 100 decimal places, it doesn't matter anymore, because I got to pick either this pixel or that pixel, and I'm limited to that. So that's where I stop my computation, because everything else is a waste of time. So, but everything's computed in terms of a distance to this, a distance to that, an acceleration of this, a velocity of that. It's all in terms of distance, not in terms of counting pixels.
Okay.
I don't think even when they show you a picture on your screen, they probably are measuring distances and then have some conversion, some chip that's made that takes that position and turns that into the closest pixel that you can get to that position.
Okay.
But nobody says something's 10 pixels over and 6 pixels up. That's not how you generate a reality. You generate a reality and say, here's a distance. Now that distance will land, and that's the closest pixel. So that's the one you put it in. So you might move it a little bit, left or right or up or down or over to get it in the closest pixel you can find. And in that case, if your pixels are tiny little cubes or tiny little spheres, it really doesn't matter too much.
Okay.
It's just going to land in that pixel. And you might always land it in the center of that pixel, in which case the pixels, the pixel shape is irrelevant.
Right.
So you'd always have your vector end in the center of a pixel.
There's actually an argument by Herman Weyl, contemporary of Wheeler, I believe.
Mm-hmm.
An argument for why space time cannot be discrete, and it is based on the idea of counting the pixels. And he says that if you have a right triangle made out of pixels, you don't get Pythagorean's theorem.
Right. Exactly. Because Pythagorean theorem requires continuous space.
Right.
So do all of our mathematics that we call analytical mathematics. Analytical mathematics means that it's continuous space. They're analytical. They have equations. Now we have another way of computing things, and that's in a computer. That's different. Now, when computers compute things, they don't compute that way. They calculate distances and so on, and then they stick them in whatever pixel happens to be what they've computed, rather than counting pixels over and down. So I think that's the difference between it.
Yeah.
Is that analytical mathematics has no discontinuities in it. Everything's smooth. But in digital computations, you can have a line going here, and it just stops there and appears up here next. And then from there, it goes over here, it makes right angles. Right. Whereas in our natural worlds, you hardly ever see a right angle. Everything is kind of smooth and continuous functions. And all of our calculus, you can only integrate and differentiate continuous functions. All of our mathematics is only for continuous things, because we believe that we lived in a continuous reality. So time and space were all continuous. So all of our mathematics has been developed for continuous functions. And when we have to deal with discontinuous functions, generally we need a computer. Or we need to have what's called boundary values, where we get to a certain boundary and we stop, and then we change initial conditions to another point, and then we go off with another piece of continuous stuff here and that. So we can have discontinuities with what's called boundary value solutions to model discontinuous things. But in computers don't care. Computer can make a line this long, do a 90-degree turn, and make another one that long, and calculate the distance between them. It lives in digital space, and consciousness it's a digital system.
Mm.
It's an information system, and digital is just, digital is again, my larger conscious system is a metaphor. Don't believe that that's a thing. Oh, there's this little old man with a long white beard called the larger consciousness system. Trying to make it into a thing like that is a mistake. It's much better just to say it's an information system, deals in information. What's the smallest piece of information? A bit. Okay, so you have a digital system that works with bits. So it's just, without trying to, make it more human or make it more anything, just kind of leave it like that. Yes, that allows for a lot of uncertainty. It's not specified precisely. It's just specified by its attributes. It's an information system. Smallest piece of information is called a bit. So it runs on bits. It's a digital information system.
Mm.
And so you look at its attributes, but don't turn it into like one of our mainframe computers. It's not necessarily like that. Within consciousness, there is no distance.
Right.
Now our little mind says, what does that mean? And we try to imagine that. What do you mean there is no distance? And basically it just doesn't compute. We can't think that way. What does it mean that there is no distance? That's there is no things are not continuous. But so we have to just let that be. So LCS is a metaphor for the source, and the source is information, and information comes in bits. That's why I say it's a digital information, because that's just how information is described. The smallest piece of information is a bit. Otherwise, you can't describe information in detail of how it's made up. So all of these are just models. They're not facts in the sense that, oh, there's this thing out there, and for some kind of magic that nobody can understand, there is no distance. You just can't go there. It doesn't work. You have to just look at the attributes and say that's what it is, because again, it's a model. That's what it would have to be in order to do the things that we see it doing, in order to explain all the facts that we see. And okay, it explains quantum physics, and it explains relativity, and it explains all these things, and it solves all these paradoxes. And so we look at it and say, well, if it does that, then it must be a good model. Doesn't make it a correct model, doesn't make it a fact, doesn't make it the model that will never be changed or added to, ever, a law. Doesn't make it any of those things. It makes it a model that fits better than any other model we happen to have right now. That's what it is. We don't want to make the same mistake that, that made electrons facts.
Right.
Yes, there's all these little like BBs and they're running around in your wire. No, that's not true. If you try to use that, it breaks down, but it acts as if there were points that had charge. Yes.
Right. In philosophy, I think they call it abductive reasoning, which is the inference to the best explanation. So you're not saying it's absolutely this model is correct. You're saying right now this one has the most explanatory power. It makes the best predictions. So this is the one that works best.
And I don't think science can ever go beyond that. I think that's the whole point. Only if we believe we're in a materialistic world that's just full of facts that are just there and that's the way they are, well, then, yes, you can have a science that, tells you exactly how things are, and those things can't change. But we don't find our reality to be that way. Quantum physics just blew that concept all to hell when the double slit had these particles rearrange themselves for no apparent reason into a interference pattern of all things. And why that particular interference pattern? Well, because it matched up with optics. That way, there wasn't an inconsistency between optics and quantum physics, because otherwise there would have been, because photons are non-interactive. Photons don't interact with each other. So it doesn't matter whether you have a million photons, as in a beam of light, like in optics, or just one photon, as you have in quantum physics. You got to get the same answer because photons are non-interactive. Well, that's a problem. So when the system finally realizes that there's some smart physicists that are putting one at a time into their system, what are they going to do? They're going to give it that random draw from the probability distribution of the possibilities. That probability distribution they're going to draw from looks exactly like an optics interference pattern, because that way there's no discrepancy between the two sciences. The two
Right.
sciences will agree. So that's why you get that. So when fire a particle, random draw from that probability distribution, eventually you take enough random draws out of that probability distribution, you create a pattern that looks like that probability distribution. And why did the system pick that? So that it would have a consistent story here. It
Right.
wouldn't have a logical problem. So there you go. That's quantum physics, and that's why quantum physics is like that. And what does that do? Once you understand that, you have to also understand that, oh, there's an intelligence in charge here.
Mm.
Oh, it can pick whatever probability distribution it wants. It has, it's not only intelligence, but it has some, what do you call it? It can take actions. This is a virtual reality. It's computed, and there is an intelligent, a conscious computer, a computer that is conscious, that is creating it, because that takes thought. Oh, this is going to create a problem. I need to put a very specific kind of probability distribution here to take those random draws from. Otherwise, I'm going to have a problem in my virtual reality. So it did that. So now that gives evidence that, consciousness is the computer.
Right. Yeah, that was a question I had for a while, and when I heard you explain that for the first time, it made sense. So I have one last question for us. We're a little bit over time, but this one I think will be okay. So one thing about both quantum mechanics and relativity is, for the first time, they introduced the observer as an important thing. In relativity, you have the speed of light is constant relative to an observer, which is very interesting. And to me, it's also kind of points to the fact that this is a virtual reality. So one
Yes.
question I have is, so Immanuel Kant had this idea that space-time is kind of intrinsic to a human mind. It's like built into the human experiencing mechanism, I guess. And how you were just talking about how it's impossible for us to even imagine what it means to say that there is no distance fundamentally for the larger consciousness system. Um, so, so the system sends each of us a data stream that is what we experience as reality. Um, and I guess, is it the case that we each have our own space-time coordinate system that is being rendered to us, and these moving relative to each other is what results in the Lorentz transformations and the relativistic effects that it has to correct for these multiple separate space-time coordinate systems with their own speed of light being constant to them, moving relative to each other? Is that what's going on?
Yeah, I think so. That's basically what's going on, in that um, if you if you're right, if the reality you're in, if the coordinate system you're in, I guess would be the right thing to say, you know, that has a delta x, delta t, just call a reality frame if you want. That has a delta x, delta t, and the speed of light can't go any faster than delta, x over delta t. So that fact, just that you're in a coordinate system and that the speed of light is limited, can't go any faster, can't go any slower. It always goes that same speed. But you can move relative to that. So you can be going, as you approach the speed of light and the signal's going the speed of light, it takes it a longer time, to get to you. Or if you're going toward it, it takes a shorter time to get to you. So you see things happening sooner or later, depending on your speed relative to the speed of, the light signal that's sending you some information of some sort. And it's just that thing. It's the relative motion among inertial frames, is what he calls that. The relative motion among inertial frames, if you take that fact that they are moving in such ways that they will get information sooner or later based on their directions and their speeds, and that the speed of light is a constant, then you end up with, the Lorentz equations then tell you what that looks like from a specific observer's viewpoint. So then the time dilation, the length contraction, the increased mass all come out of the Lorentz, because you've got that denominator term of C over V square. C square over V square, something I can't remember. No, one minus V square over C square. Yeah, that's in the denominator. So when V equals C, it's 1 minus 1, and the whole thing is undefined. But as long as V is less than C, then you can compute that 1 minus V square over C square in the denominator. And that then turns out to give you all kinds of weird things because of light being constant and different inertial frames relative to that light and to the source of that light. So it's just mathematics, and it's not even very deep mathematics. It's just algebra. You don't even have to do calculus or anything. It's just an algebraic system. And when you put in the equations, you end up with that I'm trying to remember what's in the numerator of that system. But anyway, it's the I think what is a square root of 1 minus V square over C square or something in the denominator. I can't remember the details of that, but that's what gives you all the weird stuff. It's that V square over C square, the difference between those two velocities. So that just occurs because light is a constant.
Right.
If light weren't a constant, and there's all these inertial frames are all in the same reality frame, let's put it that way. Light travels the same speed for all these inertial frames. It's not that each one has its own C. They all have the same C, and it's always a constant.
Okay.
Then that's the fact. Because that light is a constant, see, everything else adds. Velocities add on everything else that we have. Right? If you have something going to velocity and they eject something in the direction of their velocity at another velocity, and it's the sum of the two. This is the way that ejected thing looks relative to the ground. I usually say you're in a car going 10 miles an hour and you put your hand out the window and you throw a ball 10 miles an hour in the forward direction of the car. From the ground, that ball's going 20 miles an hour. It gets 10 miles an hour from the car and 10 miles an hour from your throw. So velocities are always additive. Whatever the source is, the thing you eject from the source gets the speed of the source, but not light. You have a flashlight going, 0.9 C, and it turns on the flashlight. Well, the light that's coming out still just goes C. It doesn't go C plus 0.9 C. And that is the key. Everything else, velocities add. But in this case, they don't add. So now when you have things moving around and velocities don't add, you have some squirrely things that take place, and you do the math, you do the algebra, and you end up with a Lenz's equation, and you end up with time dilation, length contraction, and growth of mass. And they're all very strange things. And they all have to do with constant velocities. They don't have acceleration in them. This is all that what do they call it? Special relativity. Special relativity came first. And in special relativity, everything is just, you have a constant velocity v that's going this way, and then somebody else in another ocean frame, there's a constant velocity v going that way, and then a third thing sends them both a signal. They see different things at different times.
Right. Yeah.
They don't get the same. They don't have the same image of what things look like. So it appears as if it's shorter in that dimension that it's going. It appears as if time is going slower here. And that appears as if actually means that if you're in that reality or on that inertial frame, that's the way it is. But it appears as if to this person, that's the relativity.
Right.
So when you're in that spaceship going very, very fast, you don't realize that you're in slow time. You're just in regular time.
Right.
But from the other people who are back on Earth, they see you in slow time. And then by the time you come back, sure enough, you're still in your 30s, and all those people from Earth that were watching you are now in their 60s. Couldn't be any other way, because they were looking at you and you were in slow time. So how could you be any more than that? So it produces these squirrely results that make the world sound really strange. On the other hand, going anywhere near as fast as the speed of light is not something that people do regularly. It's kind of a far out thing. We only do that with tiny particles and big accelerators. All right, then you have to calculate the relativistic effects when you've got that particle zinging around in a cyclotron, at 9/10 the speed of light. Now you have all kinds of effects that you don't get. But as far as us in the in the physical world that we live in as humans, we don't experience any relativistic effects. So for us, it's mostly just math and situations that are way beyond our experience saying that these things happen. And then we measure them in the sense that we take a little cesium clock, it goes tick, 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 and we have another little cesium clock that it's paired to, and both of them are tick, tick, ticking at exactly the same frequency because it has to do with a crystal of cesium. And they take those two identical crystals and they send one out on a satellite and let it zing around for a while and then come back. And sure enough, it's younger. It hasn't done as many tick ticks as the other one that stayed here. So then we say, oh, it works. It actually works that way. Well, it would have to work that way. Otherwise, the math would be inconsistent. And math is a logic of quantity. Math tells you the way it appears. So the way it appears here from Earth appears different than the way it appeared from the person on the satellite. It just ticked normally. But its ticks are slower from the perspective of here. And when you get back here, they actually were slower because you're coming back to this perspective. Very weird thing for people to think about. And it'll kind of twist your mind up a little bit if you try to rationalize on that. But that's just the nature of having a single fact. And that is that the speed of light is not additive. It
Right.
just is a constant. And once you have that, all these weird things just fall out because of that one fact.
In epistemology, they have this thing called the old evidence problem. And it's this, I think it's like a Bayesian theorem that proved it or something, but it's if you get evidence for a theory before you have the theory, for some reason it doesn't really count towards evidence for the theory. So like quantum mechanics and relativity, it seems very clear to me that these are evidence that we live in a virtual reality.
Mm-hmm.
When we gathered all this evidence, we didn't have the theory yet. Now we have the theory, and for some reason, it's really hard to show people that all this evidence we gathered way back here supports this new theory. So now we have to go gather new evidence. Like you're
Yeah. It's it's a problem with belief.
Mm,
When you have beliefs, you shut out all the other possibilities.
right.
And so if you think that this world is a material-based world and it's deterministic and therefore consciousness can't exist, time can't exist, free will can't exist because it's materialism and therefore it has to be determinism. And if that's the way you believe the world is, then somebody telling you that this is a virtual reality computed in consciousness is just ridiculous. It's outside your belief. And when you get things outside your belief, you just push it away and don't even deal with it because it's obviously wrong because you believe that things are a certain way. So it's just the nature of belief that is the problem. Now, if these people had come to their materialism after Newton and saying, well, it appears as though our universe is materialistic, like a big clockwork. Everything works like a big machine. That's interesting that it appears that way. And I'll give that a 0.9 on my probability. Well, then they'd be open to something different
Mm,
that could explain things better. But it doesn't work like that. And in science, of all places, it should work like that. Science should always have an open mind. Science should just look at the facts, not, does this fact fit with my belief? No, well, throw it out, which is the way it is. A theory should be, and any good philosophy of science book will tell you that the way you tell whether a theory is good is whether or not it explains all the known facts, whether it can explain new facts, and how few assumptions does it take to do that.
mhm.
That makes a good theory, if it can explain all of those with very few assumptions. Well, period. So if something can do that, then it's a good theory, and you should drop the old one and take on the new one.
Mhm.
See, so if science were true to its scientific, methods and kind of how it's supposed to go about things, they wouldn't have any trouble with this. But they have trouble with it because it violates a very dearly held belief, and that belief, the scientists, and they look at the kind of the history of science, and they were struggling against the high priests of religion,
Right.
and they were being burned at the stake and put in, house arrest like Galileo, and they had all these issues that they had to struggle with because of belief. So they come to they finally become significant enough to be their own thing. They were just natural philosophy, right? Science used to be called natural philosophy. But then when it kind of broke out to its own field with its scientific method and so on, they kind of got the idea that anything that doesn't follow this method is trash.
Right.
You don't do this, then it's not worth thinking about. So suddenly philosophy, metaphysics, everything else got thrown in a trash can because if it doesn't follow the scientific method, then it's opinion. It's not fact. And opinion, well, could be right, could be wrong. Who knows? Who cares? Let's move on and just find the facts. But slowly they turned their new idea into a belief, and that belief has become sacred. And they have this idea that if we let that belief go, that the scientific method doesn't actually apply to everything. It only applies to the material stuff. It only applies to the physical world. It doesn't apply to the consciousness world. It's limited. Well, what they say is, well, then consciousness doesn't exist. Well, that's silly for a whole bunch of conscious people to turn around and say conscious doesn't exist, is kind of a stupid thing to do, but they do it anyway because they don't have any choice.
Right.
That's it. Or say that, they have to include consciousness as part of reality. And now their scientific method doesn't apply. And it doesn't work out like that because now we're talking about things that are in individual minds. Everybody doesn't get the same answer. It's just, every experiment doesn't turn out the same way. It's just because we're talking not about objective, but subjective reality. And to kind of write that off as it's not important or it's all hallucination is a huge mistake. It's the most important part of our reality. The stuff isn't the important thing in our life. It's the relationships, it's the connections, it's our values, it's all that stuff. Justice, caring for each other, all of that is important, much more important than the stuff.
Right.
But our science says stuff is the only thing there is. All the rest of that stuff really doesn't exist. And that's, from your viewpoint and mine, that's obviously wrong. All that other stuff not only exists, but it's a major part of everybody's life. You have to take that into account too, but the scientific method doesn't apply. So now we're lost. Nothing can be done. So we'll just ignore it. But that's not true. Something can be done. You can understand it. And, the model I bring to science does understand it.
Mm-hmm.
Does say that it is something you can do. It comes up with kind of a science of the subjective. You can look at people's mental states and look at them in terms of fear and love and entropy and so on, and you can know a whole lot about them and how they make their choices and why they make those choices. And there's a lot of information there that you can gain in the subjective world from this model. But again, the model is just a model, a theory, and should never be taken as the fact, because then we're just back in the same boat. And 200 years from now, they'll be trying to escape from that belief. So it's better just to not make it a belief. But the science community does not pay attention to their own words. They do not look at theories based on how good the theory is, as far as does it answer the male, does it, they look at a theory on the first, does it support materialist viewpoint?
Right.
And if it doesn't, they throw it out without even looking at it or considering it, because by definition, it must be wrong.
Right.
So they are just in the same position that the high priests were, back in the 15th century, that the Galileo was, having a hard time with. They've put themselves in the exact same position now, doing the same thing that those high priests are. They're doing the exact same thing, and eventually science got out from under that religion, and someday we'll get out from under science. Or science as we know it now will just change. Science will become bigger and
Right. Yeah.
less, with a larger viewpoint.
Right. Yep. It's a bit of an overcorrection from being under the thumb of religions, but
A step forward. I mean, we had to go in that way. Unfortunately, people didn't have to have the fear of the unknown kind of squish them down into beliefs and then become believers. That was unfortunate, but yeah, that happens. That seems to be the way we humans are until we grow up a little bit. That's
right.
just the way. That's just the way we are. Maybe next time we won't do that. I don't know. I hope not. But I'm trying to make it clear that this is my model is not the model, for all time. I try to make that very, very clear so we don't do that. But humans are strange animals.